we established the boundaries of AI behavior with Agent 22, the ethical reasoning agent. It acts as a set of guardrails, strictly controlling what an autonomous system is permitted to do. But ethical constraints alone do not make a system transparent. That requires a completely different architectural component. Agent 23, the explainable agent, exists to build glass walls around the internal logic of a decision engine. Consider a modern hospital network. An engineering team deploys a new diagnostic model that flags a dangerous acute condition with 95% accuracy. It is a highly capable tool, yet on the hospital floor, adoption hits a brick wall. The physicians refuse to use it. The doctor rejects the recommendation because the computer said so is not a clinically valid justification. The physician must sign their name to the chart. If they cannot verify the evidence and the logic behind the diagnosis, they cannot ethically act on it. There is a massive operational divide between a model that is mathematically right and a system that is trusted by a professional holding ultimate legal liability. This trust gap is the primary bottleneck for enterprise AI. We see the exact same rejection pattern from loan officers, legal teams, and compliance auditors. Raw predictive accuracy is insufficient. A model that cannot explain its internal reasoning in terms a human can audit is practically useless in a high-stakes environment. The industry often attempts to solve this problem by bolting a natural language prompt onto the end of a pipeline, asking the model to explain its reasoning. This is a dangerous anti-pattern known as post-hoc rationalization. In a post-hoc setup, the system makes its decision first. Then, a separate prompt asks a large language model to justify that outcome. The LLM does not trace the actual mathematical execution. It simply uses its training to invent a plausible narrative that fits the result. This mechanism triggers an inherent risk native to foundation models, the illusion of confidence. Large language models are optimized for fluency. They are highly articulate. When forced to rationalize a decision, they will generate a confident, authoritative explanation, even when their underlying logic is entirely fabricated. They become confident liars. In a hospital triage unit or a bank's risk department, an AI that simply outputs "I don't know" is safe. An AI that manufactures false trust by presenting a coherent but invented explanation is actively destructive. Global regulators recognize this danger. Under frameworks like the EU AI Act, Article 86 grants individuals a legal right to explanation for decisions that adversely affect them. Opaque black box models and post-hoc guessing do not satisfy this requirement. True explainability cannot be a text filter added as an afterthought. It must be engineered directly into the agent's cognitive loop as a real-time architectural primitive. This chart diagrams the trace-to-trust pipeline, a 6-stage architecture designed to neutralize the post-hoc trap. Instead of guessing after the fact, the agent runs a parallel transparency layer. As the agent processing data, this layer quietly records an immutable trace of every single cognitive step. Stage 1 is input analysis. The agent parses the incoming data to evaluate the operational stakes of the request. A system parsing a dataset to recommend a movie requires a very different level of scrutiny than a system parsing a credit history to deny a mortgage. The agent triages its own risk profile immediately. Stage 2 is rule and risk logging. As the agent moves through the decision tree, it drops permanent snapshots of its internal state. The system's decision logger explicitly writes down which specific domain rules fired, what weights were applied, and which alternative options were discarded. This happens in real time, eliminating any need to generate a narrative later. This is the Python implementation. By explicitly tying the decision logger to the apply rules and assess risk functions, the code hardwires transparency into the execution loop. Capturing the state dynamically guarantees that any explanation generated downstream is mathematically faithful to the agent's true behavior. But recording the logic only solves half the problem. The most complex technical hurdle is quantifying certainty. A raw probability score generated by a model is inherently untrustworthy. This critical vulnerability is addressed in Stage 3, confidence calibration. If a model claims 99% certainty on a prediction, but historical logs prove it only gets that specific class of problem right half the time, the confidence score is miscalibrated. It is lying to the user.
We correct this using mathematical mechanisms like temperature scaling. This process recalculates the raw logits, physically dragging an overconfident, uncalibrated guess down to match the system's empirical track record. The system also splits uncertainty into two categories. Epistemic uncertainty means the agent simply lacks the training data to know the answer. Aleatoric uncertainty means the event itself involves inherent, irreducible randomness. The architecture enforces a strict sequence. Calibration must execute before any natural language is generated. In this code block, the raw score passes through the calibrator first. The text generation layer is locked out until an honest probability is assigned to the hypothesis. Forcing the agent to quantify its uncertainty strips away the illusion of confidence. It transforms an arrogant black box into a cautious, reliable advisor. Once the decision and its confidence score are finalized, Stage 4 secures the record. The complete trace block is written to storage. It is an append-only, write-once record. It is secured with a cryptographic hash and permanently tagged with the exact model version used to process the request. This functions exactly like a flight data recorder. If an automated decision negatively impacts a user, an auditor can extract the hash and forensically replay the precise variables that led to the outcome. Stage 5 is audience explanation. The system takes that single, immutable trace and renders it for human consumption. Different stakeholders require completely different translations of the exact same mathematical log. A one-size-fits-all summary fails to build trust across disciplines. The generator outputs 3 distinct tiers: a complex SHAP feature attribution table for the machine learning engineer, a list of clinical differentials with citations for the physician, and a plain language summary of action steps for the patient. Finally, Stage 6 acts as the architectural gatekeeper, safety escalation. If the calibrator registers a low confidence score, the system physically breaks the automated loop. It refuses to output a decision and automatically routes the trace data to a human operator. We map these thresholds directly in the code. An internal confidence score dropping below 0.7 triggers an immediate halt, replacing the output with a mandate for human review. The trace-to-trust pipeline converts an opaque verdict into a legally defensible record. By tying multiple audiences to a single mathematical truth, it creates an autonomous system that defaults to human safety. To see this architecture operate at scale, we look at the medical diagnosis assistant. At the edge, biometric and symptom agents process local data, feeding structured findings into the diagnostic coordinator, which synthesizes the evidence and appends its explained, calibrated trace to the final report. However, this architecture has a strict operational limitation. Agent 23 guarantees that a system's logic is explained faithfully. It does not guarantee that the logic itself is flawless. If a wearable biometric sensor malfunctions and feeds corrupted heart rate data into the pipeline, the system will process it. The explainable agent will then faithfully output a highly detailed, transparent explanation for a completely flawed medical decision. Transparency is not a substitute for data integrity. Agent 23's job is not to miraculously fix a bad decision. Its job is to make the reasoning visible enough that a human professional can catch the hardware error before it causes patient harm. With the explainable agent in place, the governance and safety tier is complete. We have bounded the system's behavior with Agent 22 and rendered its internal logic auditable with Agent 23. These two agents operate as strict, non-negotiable prerequisites. Without them, deploying an AI agent into a regulated sector is an unacceptable liability. Now that the governance layer is established, we can build systems that execute high-stakes domain work, beginning with Agent 24, the Healthcare Intelligence Agent. Agent 24 takes the exact explainable foundation we just built and pushes it directly into the demanding, high-risk environment of a hospital operating room. To review the complete code implementations for Lyme, SHAP, and the temperature scaler, read Chapter 12 of 30 agents every AI engineer must build. In enterprise AI, raw accuracy is cheap. Transparency and calibrated certainty are the only currencies that buy institutional trust.